This conference will now be recorded.
Hi, good morning, everyone. Hope you're able to see my screen as well as you're able to hear me well. Please confirm.
Good morning, Madhu. We can.
Okay, good morning. Hope everyone is doing good. So, hope all of you are also in comfortable positions, adjusted yourself to try some code. Okay, so we are doing a toy project, and the intention of this toy project is to build an intuition around the most important concept of machine learning, and that is model complexity. So we started, this is the third session we are doing our continuing on our toy project. So we have created our own data set and we made it a little bit more realistic by adding random noise, though because we created the data with one input feature and one target variable, we know already the underlying true relationship between the input feature and the target variable, but we intentionally added some random noise to that, and then using that data we are trying to build models of varying degrees of complexity and figuring out whether a particular model's predictions, based on that we are judging the model whether it is an underfit model or an overfit model. That's what we have been doing. So in the previous session we built a very simple mean model which doesn't even need any algorithm, and we judged it naturally. It's an underfit model. And then actually we started applying a little bit of scikit-learn algorithms, and we took a simple linear regression algorithm and we have fitted our data to that linear regression algorithm, which internally uses a mathematical mapping function y hat equal to beta 0 plus beta 1x. And then we built a model and we overlaid the model on the scatter plot and saw, yes, it is better than the mean model because it could understand the slant in the data, but there is an inherent problem with any linear model that it actually doesn't have flexibility to understand any curvy relationships that may exist in the data because of the mathematical function that we are using. So we again judge that model as an underfit. And now in this session, we want to go forward and give more flexibility using our linear regression algorithm only, but give more flexibility by applying some polynomial linear regression and see how the models will be built and also judge them. Again, we are judging right now the model's performance by eyeballing it because it's a two-dimensional graph we are able to create and we are able to eyeball, but that is not how we actually judge a model's performance. A model's performance will be judged by predicting with some test data, and then every type of problem has its own formal metrics. So we collect those metrics, we compare those metrics, and then judge. Even in this toy project, we will do that. In the fifth or sixth lesson, we'll be doing that. But right now, we are there. Let me move on. So first, I will take you through a little bit of that conceptually. Then we will jump into the coding section. Again, we will go slow, try out all the things that we are putting on the screen, and stop me whenever you want to. Ask me to go back, all that is okay. So try to get whatever this 1 hour time. Some of you may be busy with office work. So let us use this time to even do a little bit of hands-on so that you will get that concept as well as you will be more confident. That's the goal. Okay, so just to recap, why we need to add more complexity, flexibility to our model, because the last two previous models actually were not understanding the data properly. So we have created this linear regression model, and we overlaid the black dotted line, that is our model, uh, fitted and saw that. So it is a slanted straight line. It is better than the mean model, but it has an inherent issue, limitation. And what is that limitation? It assumes linearity because of the mathematical mapping function that we are using, y hat equal to beta 0 plus beta 1x. Because we don't have polynomial terms of this x, it cannot understand even if there is a little bit of curvy relationship that is there in this data. So that is the problem. So now that is why we have built an underfit model, and this is not good. So now what we will do is that we want to add to our data set more columns. The columns are nothing but our input features. So what we will do is that there is a x input feature, we created that values, and there is a y, that is our target variable, again we created by adding noise to sign of x. Okay, so now we will add one more feature. That feature value is nothing but x square. So whatever is there, 100 values of x, we will create squares of those values and put it into a new column, new feature that represents x square of the data. Okay, when we use two features and uh, one target variable, the mathematical mapping function that will come into place by linear regression algorithm will be y hat equal to beta 0 plus beta 1x plus beta 2 x square, because we are making this x square as a new column. Okay, so this equation is called a polynomial equation. So using this mathematical function, we try to fit the data and see what happens. Okay, so this is called polynomial. So basically the simple linear regression coefficients are beta 0, that is my y-intercept. That is, when x equal to 0, the value of y, we call it as an intercept, that is always there. And then we have beta 1, this is the coefficient, the slope coefficient for the x, one feature. Okay, now we are adding extra things. So this is the y hat is our predicted value of y, and we are adding now polynomial terms. So this mathematical function, we call it a second order polynomial function. Okay, and we can so because of this x square, this is second order polynomial regression. So when you use your linear regression algorithm with a new table, the table that has value for x, value for x square and y, and you separate the input features and target, and then you instantiate one linear regression algorithm, then you model dot fit with features comma target, then it will understand this new data, two features, one target variable. Two features is, one is x value and x square value. So now after solving the problem, it will try to understand the data and fits the curve in such a way that wherever the cost function is minimum, it stops there. When it stops, this time it will throw out three coefficients, beta 0 plus also it will give beta 1 value and also beta 2 value, because I have actually two input features and also the y-intercept. All three values it throws. Now I will substitute those values into my y hat equal to beta 0 plus beta 1x plus beta 2x square. With x, whatever value I want to predict, I give that x value, and then I substitute the x and also beta 0, beta 1, beta 2. Then I calculate my predicted y's. Okay, and if I do the same thing for all x's, I do that, then I can overlay this graph. If you look at here, this red dotted line is a model created by second order polynomial regression. If you look at the black dotted line, it is a slanted straight line, whereas this red dotted line actually started understanding a little bit of the curvy nature in the data. You can closely look at it. It is not a slanted straight line. It is actually a little bit of curvy line. So now there is a scope now to understand this data by having the polynomial terms and fit a linear regression algorithm. We may be able to understand this data better. So then we will increase the polynomial terms now. Let's say we want to use third order polynomial regression now. So basically I want to add one more feature which represents x cube. So I have a column x, I have a column x square, and I will have another column x cube. So three input features and my y hat. So again, I fit a linear regression model to this. Then it will search through the space and fits the best curve possible through the data. And at the end of that, after it found out the optimum curve, it will throw out four coefficients: beta 0, beta 1, beta 2, and beta 3. And now I will substitute for a particular prediction x value and all these beta 3s for the best fit line, and I will calculate this. So I can predict using that, and I will calculate for the same x values, 100 x values, and overlay that. Then I can see such a model now. Whatever my red dotted line is my best curve that was understood by my algorithm uh, to understand this data. So this is a much better representation of our true underlying relationship that existed between my x and y. Then I can keep on increasing my polynomial term. Again, by eyeballing, I can say that this is a good model actually. It is almost going as a sinusoidal wave. That is what we know. That is our true underlying relationship. But again, as I told you, in such simple problems, through an eyeball, we can tell this is good model, well fit model. But then we have to do a proper empirical evaluation, which we will do. Okay, but this appears to be a good model. Third order polynomial regression model seems to be a good model. Then I can be more greedy now. Okay, yeah, I'm able to capture these curves. Why not I increase my polynomial order? And let's say I fit using x one column, x square, x cube, x to the power of 4, on and on and on, x to the power of 9 and x to the power of 10. So I'll add another 9 more columns representing the values of x, x square, x cube, x to the power of 4, x to the power of 5, and so on and so forth. Then I run my linear regression model. Then it will fit this kind of equation. Then if we plot that, we can see this kind of model it has fit. This model understood the curves, but there is a problem at the edges where it seems to be understanding also some noise. It is not a pure sinusoidal wave, but towards the edges it is curving because it is driven by noise. Because we have given a lot of flexibility through 10th order polynomial. So because of that flexibility, it not only started understanding the true underlying signal, understanding relationship, that is what signal, but also it captured some noise. So these are typically underfit, overfit things. So we have seen now, we have started with a simple linear regression, now adding polynomial terms and applying that regression model, how things are changing. As you are giving more flexibility than it is required, it is capturing noise. At a right level, it is trying to understand the data well, and those models are the best models. We have to not go after the underfit model. We also should not go after the overfit models. That is what is the game we play as machine learning engineers. So that is what we will do. So in summary, our third order polynomial regression appears to be the right level of complexity for modeling the sine wave. Okay, at least by seeing it is appearing, but we will confirm it as well. So now let us get hands-on practice with these concepts. We will build all those things now, and we will see for ourselves on our Jupyter notebooks. Hope all of you are ready with your Jupyter notebooks. Whenever you are facing problem, that's what I hear from some of you, 100% it is actually typographical mistakes you will be doing. That is one problem. Because of that, some errors will come, so check that carefully. Other thing is that some of the cells you may not have executed. Last time you executed, this time you opened, copy pasted, but you are directly going to our code and executing only the 10th cell. Then actually problems will come. You have to execute all the cells every time, because as soon as you switch off kernel, all that context is lost from the code point of view. So that's why be careful, but I will go slow. You can follow with me. So what we will do in this coding is that we will take a look at polynomial linear regression, which actually by inherently they understand curvy lines to the data. Okay, so we use first second order polynomial, so it will use this y hat equal to beta 0 plus beta 1 x plus beta 2 x square kind of thing. So basically what we have to do from a coding point of view is that we have our simulated data set which has one column x, another column y. We want to use this kind of function, then I have to create one more column which is nothing but x square. So we have to do that and then run our linear regression model and then plot it. That is what we have to do. Similarly, if I want to increase the order of polynomial to third order, then I have to add one more column to my table that is representing x cube values. Then you run your linear regression algorithm, then it will try to fit this kind of equation and come up with these coefficients, or we call sometimes these betas as model parameters. These are learned by your algorithm based on the data you gave. Okay, so if you give a different data, different betas will be calculated. Keep that in mind. Okay, any questions so far? Shall I move forward?
Yeah.
Okay, please stop me whenever you have anything in your mind. Okay, so let us start. Anyway, this is our header. Always let us start. If you have already that, have that copy but into a new file and run that cell. But this time I am putting, because we will be using this linear regression algorithm only for solving the problem. So do this also in your header from sklearn dot linear underscore model import linear regression, caps L caps R. This is our algorithm name, and this algorithm is in a sub library of scikit-learn that is called linear underscore model. So rest of the things already you have, just copy paste them and run that cell and tell me once you are ready. Are you ready?
Yeah.
Okay, so without problem the cell ran means you have imported all the libraries, so your installation is there, correct? So if some people are facing problem here, means your installation was not very perfect, so you have to uninstall and redo the installation. We started very early in our lessons. Okay, so let's move. So now this particular data set is our synthetic data set we created. You saved it into your file by using that pd to CSV function. Now read it from CSV and call it as df. Whatever you call, keep remembering that. But I have called here df equal to pd dot read underscore CSV. This pd method function will keep on using. It reads a CSV file and assigns it to a data frame called df. Okay, we can play with that using our pandas instructions. And see for yourself the first 5 observations by running this df.head function. So it will give you by default the first 5 observations of your table. So our columns are small x, y. This is my input feature and this is my target variable. This is what we created on the first session. So you have that now because we want to build on this, whatever we are going to build. Are you there?
Madhu, Joseph here.
Yes,
Can you go
Yeah.
back to the previous slide for just a minute? Yeah, just give me a minute. I'll just take this.
Yeah, not a problem. Please stop me anytime.
Okay, Madhu. Yeah,
Okay,
thank you.
okay, fine. So, so if we have done this cell, then you will see your data set imported now to your DF. Is it done? Can I move forward?
Yes, sir.
Okay. So now we have our data. So what we'll do, let us fit a second order polynomial model to the noisy sine data set. Okay. So that is what we'll do. So first, because we want to now really, if we want to make this, I have to add one more column, which is representing the x square. Whatever x is there, I have to square it and put it in the column. And I have to create a new table, x, x square and y. And then I have to run my linear regression algorithm on that. So what we'll do is that we'll make a copy, okay, of whatever df, so that the df x and y is always intact. Okay, whenever we are changing, it's always a good practice to make a copy of that and use that copy instead of tinker the previous one. Okay, so there is a very useful function to copy. Keep remembering this. So there is nothing but df.copy method. Okay, and it makes a copy of that, whatever same thing, and I'm actually assigning it to another variable name. Here I called it as df underscore copy. So always again give some names. If you are making many copies of many things, always give some names that you can easily figure out later on. Otherwise unnecessary confusion will come. Okay, so if you have done this, so your df underscore copy is just a copy of the original df. Okay, now henceforth whatever we do, we'll do it to df underscore copy, that variable. Everyone did this? Okay, so next we will engineer. So we are using a word engineer. Okay, that is what feature engineering. Anything you are doing to the features, adding, removing, combining few features. Okay, all those activity in machine learning, we refer to that activity as in feature engineering. So that is why also here we have used, we will engineer the x square feature. So we are adding a feature to that. So we will use np.power function. np.power function, how it works, np.power, whatever is the column, and you give the power 2 or 3 or 10 or 100, whatever you give as 2 arguments. One is the data, that column, and comma the power. So we want to do x square on df.x. So we want to create. So here if you carefully look at it, I am df underscore copy with this square brackets index operator. I am adding a new column. So by doing that itself, it puts a new column with a string x2. This will be the name of my third column to the table. and it will be populated. I'm equating it with populate with np.power and df underscore copy.x. I'm anyway, both of them are same, but I'm using that, and power of 2 I'm using. Okay, so understand this, because you're creating a new column and populating that column with whatever x column is there. You are making square of every value in that, and 100 values of x2 are created now. Okay, if you look at now df underscore copy dot head with the default 5 observations, now you will see not 2 columns, you will see 3 columns. Okay, so have you done this?
Yeah. Done.
Okay, fine.
Madhu,
So now you go, yes.
what is the significance of 2 in the parentheses?
Parenthesis power 2, it is square. If you want to do cube, x cube you want to do, means x into x value. Power is 2. np dot power is actually a
Okay.
method on we do, it's a mathematical function to the power. So df underscore copy dot x, x column, every value in x column, I want to square it and put it as x2 column. If I do 3 here, x into x into x will be calculated.
Got it.
Okay, fine. Yeah. If you want 100, then it will actually x2 column, it will do x into x into x, 100 power of x value, it will store them, all 100 observations. Okay, I'll move forward. Okay, you see the df underscore copy dot head. So now you are seeing x, y, this is the original df. Now we added a new column x2, which is nothing but x square. X square of 0 is 0. X square of 0.06 is 0.004. We can calculate and see and compare what exactly has been done. You got it? You're here, everyone?
Yes, Madhu.
Okay.
Yeah. Same digit.
So we have now a new table. Okay, we made it. Okay. Now what we have to do is that basically nothing changed. Now there are two input features, x and x2. X2 is nothing but x square value. Okay, and we want to fit this data to a linear regression algorithm. So whenever we fit, what we will do first, we have to separate, because all of our linear regression or any algorithm in the scikit-learn algorithms, to train we use dot fit function, and the dot fit function requires two arguments. One is features, another is target. So we have to separate now the input features and separate the target variable and pass those two data frames separately now. So how do I do that? We first features equal to df dot drop, then we want to drop y column, df dot y, axis equal to 0, whole column is dropped. Whatever remaining data frame will be equated to features. Target is nothing but equated to df dot y. That is what every time we'll do. So here we are doing that step, and actually, so three things we are doing. One is, let us invoke linear regression algorithm and call it as LM. Then separate features and target. Okay. Only thing, you do it with df underscore copy, because your original df doesn't have your x square column. Whatever you gave the name, you drop from there, otherwise you will be doing again the original df. Take care of that, whichever name you gave. But I gave a name called df underscore copy. Okay, and then I'm dropping here y column. We can give the column name y, x is equal to 1, the column will be dropped. Okay, and then target, we equated df underscore copy dot y to target, and we are fitting using the features and target. Did you do this? Can I move forward?
1 minute, Madhu. Just give me a minute.
Yeah, not a problem. Maybe I will also go here and open my, where is my, I'm also doing by the time you're doing. So same thing, I got it. df.head, I'm there. So I'm making a copy of that. So I'm introducing a power of x. Okay. So here just I wanted to plot what is the value of x and x square, how they do. If you look at the relationship, any value of x, a smaller value of x, when it is squared, it will become further smaller. But a larger value of x, when it is squared, it becomes very, so exponentially, it is small someplace for smaller x. As x is increasing, suddenly you will see a little bit of exponential way of curviness. You want to see here, just this is how our x and x square graph looks like. Just I wanted to see and show it to you. X cube, when we do, actually it will be slower till lower value, but suddenly it becomes much more steeper. Okay, that is how they work. Okay, so here I'm seeing my df dot underscore copy head. So now I have 3 columns: x column, y column, and x square column. Okay, so for example, the first observation actually is nothing but 0.063467, and x square should be the same. So 0.0040, that is what x square values. Somebody asked that question also. Okay, now I am actually building a model using this new table df underscore copy. So I am dropping my y column and calling it as features, and then I am assigning my y column values as a variable called target, and I am training my linear regression algorithm using my lm.fit method and passing my features and target, and then when I run that, a model will be fit. Okay, so now because you can do this anyway, I'll go back, but anyway, let me do this, and again I'll let you. Everyone came up to this step?
Yes, Madhu.
Okay, now what happens is that because it has x and x square, our mathematical mapping function is y hat equal to beta 0 plus beta 1 x plus beta 2 x square. So I have beta 0, I have beta 1 and beta 2. So when we do intercept, that is beta 0, value will be calculated. lm dot coefficient underscore, when you see that, it will throw a list of 2 values. One is for beta 1, another for beta 2. So if you look at the first one is my beta 0, 0.74072, that one. Okay, whereas for lm dot coefficient, now it has put 3. If it is 10, it will give 10 values. For third order, it will give 3 values. Okay, let me go back to PowerPoint again so that all of you can do, and finally I will also run and show you. So all of you are here, agreed, and you are able to fit a model.
Yes, sir.
Okay, so now you do this also. So basically, any linear regression algorithm, after completing fitting action, it searches through the space. It has a cost function which it uses to minimize, and once it found the optimum curve that is representing this data, it stops and throws back these values to us. means it doesn't throw back. We have to ask. So when you stopped, what is your lm dot intercept underscore? That is my beta 0. Lm dot coefficient, based on how many input features are there, that many betas will be thrown. So these are all called model parameters, okay, learned by our algorithm from our data that I have given. Okay, so we should have two coefficients because the model will have one for x and one for x square. So that is what we are seeing. As you can see, the polynomial regression is clearly more complex when directly compared to a simple linear regression because there are more model parameters. There are more model parameters to learn, which means greater flexibility in expressing patterns and relationships. Okay, you got these values?
Yes, sir.
Yeah, Madhu.
Yeah. So now when we predict, now basically I have in my table, I have x is there, x square value is there, y is there. That is the data using which I have basically trained up my model. Okay, this is my input features x and x square, y is my target variable. Now, right now what we are doing to overlay our predicted model, whatever, we are calculating y hat in the table for, we are taking x value from here. Let's say this is the first observation. We are taking x value from here, whatever x, and we have this beta 0 value and beta 1 value and beta 2 value. So I am calculating my y hat using that beta 0 value, okay, plus beta 1 and x from here, first observation, okay, let's say xi1. Then I am substituting my beta 2 and xi square, this value, actually x only, no, because I'm using square, okay. So then I'm calculating my y value, y hat value. So like that, for everything I am calculating y hat, okay, all 100 observations, substituting my x, beta 0, beta 1, I'm calculating, and then in my model plot I'm doing df dot x, and I'm predicting this. When I'm predicting, this is calculating, and that I'm putting 100 values onto y-axis. That is how we are plotting. Okay, let us plot it. Okay, so plt dot scatter, you give again df underscore copy dot x because you have changed the table. Actually x is same from original df also, doesn't matter, but still. Okay, then you are doing plt dot plot. My x-axis is my x values, as I told you. Y hat value I'm calculating here. How I'm calculating? My lm dot, already model has been built by fit, model dot fit thing. Then the same thing I'm using to predict, and I'm passing features. Features is nothing but my x column. Okay, and that values whatever it is calculated. Now here it is calculated by substituting x, beta 0, beta 1 and beta 2. So that is why it is different than simple linear regression that we did last session. Now when I plot, I'm seeing a black dotted line, which if you closely observe is not a slanted straight line. It is understanding the curve a little bit. Clear? You got up to here?
Yeah, Madhu. Got it.
Okay. So now we are seeing some flexibility given to our model by choosing to add the polynomial terms, and then it started up understanding curves actually. Okay, now we will increase the complexity by making it third order polynomial thing. So let me go back to my code again. Okay, so here I will also do this. So, and I have also done up to here. Okay, now if I look, my df is having x and x square. Now my goal is to build a third order polynomial model I want to build for this data. So what I have to have in my table, I have to add a new column called x cube. Okay. So what I did here, I made a copy of df underscore copy because it has already x and x square. I want to add x cube to this. What I did here, I made a copy of that df underscore copies copy, and I named it as df underscore third order. Okay. And in that, I'm adding a new column and calling it as x3 and populating using my np.power to my, how I'm doing that, whatever I'm picking values from my x, df underscore third order dot x column, that is the values I'm picking up. And for each of the element wise, I'm making a cube. X is multiplied 3 times. And if I plot it, the value x and x cube, how are they going? We can see. Okay, that is what I have done here. Okay, so again, x cube will be small for more time than x square, and then suddenly it picks up. Anyway, to understand why this curvy relationship is being understood and all, I have just put it. We'll come to that later. But so now my third order head I am seeing. So I have created third column. My input features are x, x2, x3. These are the 3 columns are my input features, and my target variable is y. So this data I will pass on to a linear regression algorithm and ask it to understand this data, fit it, and then I want to make predictions and plot it. Okay, that is what only I'm doing here. So basically, I'm doing, I'm instantiating a linear regression model, and I separated my features and target from my this table df underscore third order drop, and then it has fitted the model. Now I want to see my model parameters. What is my intercept? What are my coefficients? Now coefficients will be 3. Okay, this is beta 0, that is minus 0.2660 is my beta 0, and my beta 1, beta 2, and beta 3 are this. Okay, so now when I do predictions, my y hat will be calculated x beta 0 plus beta 1 x plus beta 2 x square plus beta 3 x cube. So these values will be substituted, and my y hat will be calculated in the lm dot predict features. And then when I run it, then and overlay my model, this is my third order polynomial function is coming. So now anyway, this is how we can write, copy this table, then separate out features and target, then you build the model, predict, overlay, plot, all those things we can do again and again and again and do it. But that is where we can use a little bit of our Python skills to solve this problem, so that we can play with those user defined functions in a good way, and without wasting time we can try many models with many polynomial terms. That is why we will not do like this. Though we can do like this, it is not very clever way of doing it. It is not really leveraging the Python knowledge we gained. We can do be more creative. So whenever in your work as data scientists or machine learning developers, whenever you have to play with it, same things but play with some different variables at a time, then pause for a while, think about how I can put together as a user defined function, and then I can call that function and do with one line. I can see the results very fast, so that I can focus more on analysis rather than unnecessarily typing same code again and again. Okay, So to do that, let us talk about some helper functions. Okay, that is where, so though I'm not making you do for x cube, x to the power of 4, x to the power of 5, x to the power of 10, we will do after writing some user defined functions. Clear? So far clear?
Yes, sir.
Okay, so let's move on. So we want to first, there are some common things we are doing. Okay, what we are doing, we are making a copy of df. First, actually, simple plotting what we are doing, fitting and plotting what we are doing. Whatever df I have, whether it is having 10 features and one target variable, whatever, I'm taking the df and separating my features and target variable and calling them features and target separately, and then I'm actually instantiating my whatever linear regression algorithm. Then I'm using lm.fit. Then I'm doing plt.scatter with whatever my df x and y. Then my plt.plot, I'm doing df.x on x-axis, and my lm.predict features, and with a separate color I'm doing it. So again and again we are doing that. So can we think of a function, because we'll be using it again and again, instead of typing so many times or copying, pasting and making errors, why don't I write a fit and plot model? I'm calling it as my function. What it does, it takes a data set and a model instance as argument. So two arguments I'm telling. It should read a df, and it also should read an algorithm. Here it is, in this case it is linear regression. Okay, but it can be decision tree in the next session. Whatever, it should read a model class as argument, and then whatever df it took, it should be able to split input features from target variable. Then it should do for that whatever model has come as an argument on that algorithm dot fit you run, and then you plot the scatter plot, and then you plot the overlaid model for predicted values of y, and you return the fitted model. This is the function we want to create. Okay, so it is not a very complex function. Okay, anyway I will show you, but how do we think fit and plot model? Okay, this is my function I want to define. Okay, so how do we define? Whatever Python we have already learned, we use def statement. Okay, then whatever name you give, but I am giving here fit and plot model. Okay, that is my name of this. So whatever arguments I want to pass, I am passing my arguments here. What I want to give, a df I want to give, whatever df I want to pass. Then also I want to pass a model class. Okay, let me call that as model. Okay, now right now we are passing linear regression, but tomorrow's lesson we will pass decision tree algorithm there. That's why we are passing one df model, so it can work any kind of situation. That is our goal. Then usually the syntax, whenever we def, it ends with a colon, and then next things will start from a tab space. We all learned while doing our Python flow and functions. I'm just bringing it. So what is the first step I want to do? I read, this is how template of my function. So first I want to read this data and separate out features and target, because again and again I'm doing that. So I'll do features, okay, equal to, I will use my df dot drop. Okay, and I will drop my y, whatever target variable column name, and x is equal to 1. So my resultant is features is there. So I'm reading it, whatever df comes, whether it is 10 columns or 5 columns or 2 columns, it does that. Okay, and then what I want to do, target. Okay, target equal to my df dot y. So I every time I'm doing, so I'm putting it into a function. Then what I'm doing every time, whatever model is coming, if it is a linear regression, I'm instantiating and dot fit. Now some model has come. Now any model, let it be. So what I want to do is that whatever is that model, I am doing model dot fit. Okay, you can also type this code. What are the things we have to pass? Features, comma, target. So it will, this is the process using which we train our data, the model. Okay, then what we are doing every time, once it has fit, we are doing the plotting of that. Okay, so first we are doing plt dot scatter always. Okay, plt dot scatter, where we are just putting our x and y values, df dot x on the x axis, comma df dot y on our y axis. After that, what we are doing overlaying my plt dot plot on the x axis. Still I am keeping my df dot x, but on the y axis, what I am doing, I am using my model dot predict, because here it's model is coming. On that I am doing predict, and I am predicting only for the same x values, not new x values, same x values, and calculating my y hat. That's what we are calling as features. Okay, and we are using a different color. This is what we are always doing, and then we are telling plt dot show. Okay, so I'm putting all these into one single function, and maybe at the end you return a model. Okay, so this will be a very useful function for you. Okay, so that is what is done here. I just wanted to you to keep thinking, because anyway this function solves this problem, but you will encounter different kind of problems, different kind of tricks you have to apply. Think through functions always, develop that thinking ability. Okay, so type this. Already you have typed, let me know, otherwise take some time and define a function called fit underscore and underscore plot underscore model. You name it whatever you want. Okay, and there we are thinking through two arguments that will be passed. One is the data frame and another is the model class. Okay, so then commonly every time we are doing this features and target split, we are doing that. Then we are fitting using that features and target. Then we are creating a scatter plot of df dot x and y. Then we are overlaying the model that has been created by having x-axis x values, y-axis we are using model dot predict with features. Hope you understood. Anybody completed this? Okay. Got it?
Yes, sir.
Okay, so anyway, we created a function we will use it along. Actually, now our problem is that we want to experiment very quickly with any polynomial. We want, right now what we are doing, we have a x and y kind of table. Based on what polynomial terms we want to add, I'm adding those many columns with those that kind of particular values of power, and then I'm separating features in target and then fitting it and plotting it. That is what we are doing. Now we have to still solve this problem of passing this polynomial thing also. Okay, so this can be a sub function. Keep that. Another function. Now let us anyway confirm whether your function is working or not. You just fit and plot your model. Df underscore copy you pass as your df, because that has two columns, x and x square, and you pass your model as your linear regression algorithm. So just notice how we are giving linear regression. Parentheses have to be there for that because it's a function class. Okay, so test whether your fit and plot model, when you are calling and passing arguments, whether it is working or not. So with single line you can achieve this. Now you can see immediately the pictures after doing it. Is it working?
Yeah, it's working.
Okay, so we have a very useful function. We don't need to unnecessarily break our head, make mistakes while typing. If it works, it's good for us. So now, but still we haven't solved our problem, because our experiment for today is actually go till x to the power of 10 and figure out for ourselves which is overfit, which is underfit, which is right fit. So for that, we are still need to take care of this polynomial model. So once I read a df based on polynomial term given as an argument, I have to add that many columns with whatever power, and then on that table I want to do this function, fit and plot model. Okay, so we have to write another helper function. Okay, this is a little clever function. Carefully look at it. But if you start thinking, not a problem. In many ways they can be solved, but intelligently also they can be solved. As you keep practicing, you will think through that. So think about it. Okay, so what we have to really do, if the order is 1, means the x square, whatever polynomial is x to the power, the power is 1, then we will just fit and plot the model directly. That is our simple linear regression, y hat equal to beta 0 plus beta 1 x. Okay, now if the order is greater than 1, if it is square, cube, to the power 4, to the power 5, to the power 10, then we will create a polynomial terms based on an argument passed, x square. If it is 2, I will give x square, means I will add x and x square. If it is 3, an argument is passed, I will create new columns, x square and x cube. If it is 4, I will x square, x cube, x to the power of 4. Like that I want to create as an argument is passed to my function. Then once I create a table, then I will pass that table to my fit and plot model, the previous function, and then it will plot my various charts there. That is what I want to do. So how is the logic here? So here it can be little thinking we have to do, but let me think about it. Actually, I know, that's why I'm thinking. You don't think that you are not able to think, I'm able to think. It is my advantage that I know everything before I'm showing it to you. So I will create a def and I'll call it as fit and plot polynomial model. That is my name of the function. Okay, then arguments are same. Again, I have to give a df, whatever df. On that df, I have to add more columns, and also I have to pass my model, linear regression or a decision tree or a random forest classifier, whatever model algorithm. So I'm calling it as model. I have to pass it as an argument. Okay, then I have to pass my polynomial. What is the polynomial I want to do? So let us call a variable called max polynomial. That is another argument. Okay, By default, I'm putting it as 1. If nothing is given and fit and plot polynomial model is called with only 2 arguments, the DF and model, then it will plot my simple linear regression model, meaning my x is x only, no powers are there, no polynomial terms. So anyway, I'll end with my colon, okay, and with a tab space, I will write. So what I have to do is that I'm reading a DF. So I have to make immediately a copy of that. Okay, DF underscore copy, because that is what we did while doing this. Then we use DF dot copy method. Okay, so whatever DF it's coming to me, I'm making a copy of it. Now I will look at what is my max polynomial. So if my max underscore polynomial is default, that is equal to 1, if it is true, what I do, I don't need to do anything. I just call my previous function, that is fit and plot, whatever. I'm not using the same name, fit plot model. I'm simplifying it. Okay, I'm calling that function. What I will do, I will pass my, because that requires 2 arguments, I'm passing my DF copy and whatever model that has been passed to this argument, if it is linear regression, whatever. Okay, so that is what by default it will run. Now if else, actually if polynomial is not equal to 1, somebody gave 2 or 3 or 5, what I have to do, let's say somebody gave 5. Now my DF, let's say it is in some particular shape. Okay, x and y is there. Okay, now 5 means I have to put another column x square, another column x cube, another column x to the power of 4, and another column x to the power of 5. I have to add to my table these things. So in the else part, we have to take care of those things. If it is 5, so we have to put a definitely a kind of loop. Okay, so we have to figure out else I'm putting here. So for whatever max polynomial comes, that I have to use to create a new columns in my DF copy. Okay, so let us talk that as power, because every time when we think about loops, we have to think for a variable named variable in, then we have to think about an iterable, means a list using which I can loop through from first value till last value. So what should be my iterable? Because for 1 already I'm taking care. So maybe I have to create a list. I am creating list using a range function. That range function starts with 2, and whatever max polynomial value they have given in the argument, max polynomial plus 1, because I'm using a range function. Let's say somebody gave 2. Okay, so it will be 2 comma 2, but what we want actually 2 comma 3. Then range, what it will do, it includes 2, but it is not inclusive of 3, so it creates only one iterable called 2. Let's say I give 4 here. Okay, for range 2 comma polynomial plus 1, so 2 comma 5 it will do. So what is the list it will give? 2, 3, 4. Okay, it will create for 4, like that it creates. So that is why I'm using that. So for loop I have created. Now once I have the for loop, what I have to do, I have to, whatever that polynomial, the power, I have to take and add one column and populate using that power given in my polynomial. So what I'll do here is that, let's say df copy, that is what we are using, df dot copy. Okay, then I have to add a column. What column I have to add? X, already X is there, and let me use a space holder and tell power, that variable, whatever they gave there. that name I will give. So, okay, I'm using dot format. So I have to use now in the placeholder. I have to use dot format. Okay, and I have to fill it with whatever power, and this I have to equate it to np dot power. Okay, so np dot power has to be applied on df dot x. So here my df copy, so df copy dot x, that is my first argument, and the second argument is actually my power, whatever this variable in the for loop. Okay, if I do this, and then it takes care of all the things, then again I want to return whatever model and also my df. Okay, df copy. This can be another function. So again, what I'm telling is that whenever you are encountering this kind of repeated kind of issues, let us think through our Python, whatever we learned. Only thing you have to do is that forget about the problem for a while, solve that cleverly, and make it as a good reusable function, and then you will accelerate in your data science work. That is why using some of this power of Python is always useful, and that is why I want to demonstrate that. So anyway, now you create another reusable function. Here it is called fit underscore and underscore plot underscore polynomial underscore model. I am passing df, the model, and max polynomial by default 1. So type this. Only on the for loop, be careful, and also ensure that these tabs are all there, and if you look at it, after else return has to come back to the outdent from for. Anybody typed it? Please tell me once you are ready. Then we'll test these functions now. Anybody got it without problems? Can I move forward?
Madhu, Joseph here. I'm getting
Yes.
invalid syntax for the first line.
Which one? Def.
Yeah, Madhu. Def fit
So
underscore and underscore plot underscore polynomial underscore
that
model.
is your name. Any name you can give, but okay, you gave it. So you have put these arguments. You ended with this colon.
E. Oh, okay. Colon.
Yeah, all these functions, def and if, elif, else, for, all these things they will have child lines. So instead of using curly braces in Java, they use Python uses a colon, and then second line will continue with a one tab space.
I'm getting error in the second line. Df underscore copy is equal to df dot copy of brackets. It is telling expected an indented block.
Yeah, because after this colon, if you don't give one tab space, it
Oh,
will give an error. Python expects typing whatever the tabs and all. That is how it separates things. So after any colon, the next line should be 4 spaces indented. Then only it will work.
okay.
Yes, sir. Got it.
Okay. Okay. So anyway, as I told you earlier also, only typing mistakes. Again, initially all of us will do the typing mistakes because we are learning Python first time and typing some commands first time. So that will happen. But as practice happens, you will automatically do that. Def this colon, then you will anyways do a tab space and go. Okay. So anyway, so we have two functions. Now our life will be very easy. We can move pretty fast now. Okay. So use this function, test it whether it is working or not. So invoke this function, whatever you created now, fit underscore and underscore plot underscore polynomial underscore model. Give it df, the whatever x and y, one I created, at least first one from our Excel table, that invoke linear regression algorithm. Tomorrow we'll do decision tree algorithms also here. But then you give a power of 2, means second order polynomial regression you want to do. So whatever we did earlier, same graph should come with single line. Got it?
Madhu, if you don't mind, can you go back to the previous slide just for a minute?
Yes, not a problem.
Joseph here. I'm getting error in the last line. I don't know. Return outside function it is mentioning.
Return, again, return is
Outside function.
so basically, is it aligned with your else or not? You have to outdent to one tab space again, because after for loop, you have to
Okay.
outdent. It has to align with else now. It are one tab space from def. So if you have just because the for loop is there, you have indented df underscore copy this whole column creation. So outdent, backspace you press.
So else and return should be of the same line, right?
Yes. Here I am doing the same thing here. You can see here also. The first one I have done. Okay. So the second one is here. So if you look at indenting point of view, def after colon df underscore copy one tab space, then because everything is function, all of them are in the one tab space is there. So here copying my df, then I'm applying a if condition. Within else I'm applying my for. So it has another after else colon one. Now return should be outdated.
Madhu,
Yeah.
Madhu, the code here and the code that you showed in the PowerPoint presentation are different.
Okay, they're different. What is
Yeah.
different in that? Let me
So
go
here
back
you have
there one.
mentioned, that here you have mentioned return instead of return model. It should be the last line should be return model, and in else it should be model equals to fit and plot model.
Where is it?
Last two lines of this code and the code that is there in your Jupyter are
Last two
different.
lines.
Yeah.
Okay, let me go. Okay, so here what we are doing, this is the fit and polynomial. Okay, so here I'm using model equal to fit and plot df copy model. So I'm calling the other function. Previous helper function we wrote. Okay, uh, here, okay, return fit and plot model, df copy model we are putting, whereas here again both of them are same. I think here what we are doing is that whatever, simplifying the return model, both of them are same actually. You can write in either way.
No, actually, with the other one, I'm getting an error saying that method object does not support item assignment at else.
Okay,
Madhu, I am getting max polynomial is not defined. I don't know why.
maybe max underscore polynomial one place, max polynomial in another place. Check that. Spelling mistakes. Okay. So anyway, on the PowerPoint thing you are telling, you have here what we are doing is that after the else, the same df, because df is now extended with those columns, I am running my previous function where I am passing df underscore copy comma model. Actually, both of them should produce same result actually. Okay, maybe some other mistake you have done, but anyway, my Jupyter node, this way is it working for you?
No.
So check somewhere the syntax issue. What is the exact problem you are getting? Tell me once.
It is throwing an error saying that the method object does not support item assignment and that at the power thing, it is not taking the
At the
power properly.
np.power.
Yeah, format power that np.power, right?
This is not doing. That's what you are telling. Okay.
Yeah.
Have you
No,
put this?
both are doing, giving the same error.
Yes, means say somewhere typographical mistake you have done. You missed. Did you check your square brackets?
But my function is compiling properly. It is not throwing any errors when I'm compiling it. When I enter the values, it is throwing error.
Which here basically this one is throwing error.
Yeah.
You're telling this? Okay.
Yeah.
So your function without any problem ran.
Yeah.
Okay. Here you are giving this basically to the power 2. You are checking. So you are
Right.
giving df linear regression algorithm, comma 2 you gave. At that time,
Yes.
it is throwing error. That's what you are telling. Okay.
Yeah. At
Then,
line 12. Whatever. df dot
at,
copy x. Yeah. In else loop, when we go for in for loop, right?
yeah.
Uh,
Okay.
After that, when we say df dot copy x format power, it is throwing error at that point.
Yeah. Then typographically you check exactly you have typed like this or not. So basically df underscore copy, you are adding a column. So you have to use an index operator. So it will be square brackets. So one square bracket is opened here. At the outside, it has to be closed. In that, you are using a string x and a placeholder using your curly braces. So this placeholder will be replaced by whatever power from your iteration. Okay. So after this, you have to put a dot format again in the bracket power. Square brackets have to be closed. Okay. Again, you have to see whether this string x curly braces and close with single quote again before dot. Okay. Then we are equating it with np dot power. Okay. We are passing two arguments, df underscore copy dot x and power. Spellings again, power you have used or anything else you have used. Check that once. Check it.
Yeah, everything is same, Madhu.
Okay. Then there may be some problem before this. Okay. Your wherever we have to carefully look at it anyway. Now this code is there, you just keep looking at it. In the interest of time, I will move forward. Again, I'm telling you, it's all typographical mistakes. Somewhere you are using wrong spellings basically of variables, your dfs, those kind of things. Otherwise, there will be no problem. Simple logic only. Okay. So once you have these functions, okay, we can play with them. I'm here using third order polynomial, then I'm calling with fourth order polynomial, then I'm calling with fifth order polynomial, then I'm extending it to 10th order polynomial, and we are seeing how it is able to get more flexibility and understanding the underlying relationship and build models. Please mute someone, little bit noise is there. Please mute if you are not asking question. Okay, so let us go back to our PowerPoint very quickly again. Okay. So basically, we have done this and we have plotted using those two functions. We have plotted. Okay. So as I told you, even if you are stuck with this, don't worry. You just check your function names when you are calling again, whether you are giving the right kind of thing. Only spelling mistakes will cause problems, nothing else. Or whatever importing the libraries, these things only will cause problems. Otherwise, there is no big issue. So don't get bogged down by that. Look at from a understanding point of view. Okay, because it's already 10:20. So let's move. So now we have our helper functions, so we can plot as many polynomial variations as we want. So for this module, we are just going to take a look at 3 more: third order polynomial, fifth order polynomial, 10th. But because you have these functions working, you can give 100, 1000, whatever you want, you can give and see what happens. Okay. However, helper functions will be very useful for you throughout your data science journey. That is why we took a little bit of pain and tried to create them. So you have to develop that habit of creating this kind of helper functions. So we'll do more and more such things whenever they are needed. So once these helper functions are there, fit and plot polynomial model I am using because it's a polynomial thing. So I'm passing my df, the original df, linear regression algorithm with the polynomial term 3 means x cube. So this is the result we got. Okay. So basically this model actually looks pretty good. Okay. It actually approximates our original sine wave. That's what we have created the data with, the true underlying relationship, quite well. Okay. As you might suspect, this is probably the best level of complexity for your model, but that we are confirming by seeing, but we'll confirm by data also. Now, if I increase to fifth order, it is also a decent model, but we don't know whether 3 is good or 5 is good. We don't know unless we really do some empirical evaluation. Okay. Again, this model actually looks pretty decent. However, generally speaking, if two models perform roughly equally, so third order and fifth order, if they are equally performing, always data science tells that pick up the simpler one. That is actually in machine learning data science, that is called Occam's razor principle. Okay, if two models are giving equally good results, always choose a model with less complexity, simpler one only you choose. Okay, so because simpler models will generally be more generalizable to unseen and new data. Okay, anyway, we'll talk about it more when we see the empirical data. Okay, then we got little bit greedy now, and we used our fit and plot polynomial model with a polynomial term 10. So we are actually going up to x to the power of 10. And then what happened? There is little bit of issue in this. It has picked up noise also. This is not quite as good as our third order polynomial regression, linear regression, because the curve is tilting toward the edge values of x. So it is picking up noise through the edges here. Okay, so the model is in fact an overfit to the data set. Okay, it will be inaccurate. So for the edge values of x, it ended up learning the noise. So a 10th order polynomial regression model actually is too complex for the data set. So what we have done through this exercise is that we are playing with the same data set and increasing the complexity of the model by allowing it more flexibility and checking how it is learning. So as we saw, the mean model, simple linear regression, and second order, they were underfit. But third onwards, it started actually understanding the data much better. But as you increase to the 10th polynomial order, then it started picking up a noise. Okay, so any questions so far? We took too much time today, but I know some of you may have to go to offices, but we'll close it, this discussion. So any questions?
Sir, Ramshankar here.
Yeah,
For 3 and 5 order, I'm getting similar graphs. So
it is not
how do
similar.
you validate which is better?
No, it is not really similar. There is little bit difference. Your eye is
Yeah,
not
yeah.
able to make it. And
Right.
again, that is why through eyeballing anyway, we will not evaluate performance of models. So we will use some metrics that will do in the same project we are going to do. Okay, so that is how we will solve that problem. So there are some metrics called mean absolute error, mean squared error, then something called R squared. These are the typical performance metrics used for evaluating regression models. Okay, so we'll use them after, actually, in fact, after this session, we will increase the complexity. Still, polynomial regression is actually a linear regression model. The algorithm that we have used is same algorithm. Okay, so whatever, because of our polynomial terms and the way they interact, and these whatever betas work in different ways for change in x, because of these betas, the y is actually taking curvy roots. But still, a true nonlinear relationship, in case it is in the data, our linear regression algorithm is incapable of doing that. So we have to totally change the way we build models. We have to let our model understand the true nonlinear relationship that might exist in our data sets. So mathematical mapping functions are not so good to capture true nonlinearity. So to make it possible, we have to change our model itself, model of learning itself. So we'll be using a computational model by name decision trees to capture the true non-linear nature that might exist in our relationship between input features and target variable. So the next session, we will change the computational model. So far, we have used mathematical mapping model and algorithm around that. Now we will change that itself and build for the same problem decision tree based algorithms and see how they behave. Okay, and then compare all of them after that. Okay, so anyway, Mr. Ramshankar, that is what my answer, but just hold on. By the time you complete this project, we'll know this. Okay?
Right, sir. Thank you. Thank you.
Yeah. So any other questions? Any other comments? If again, those who could not completely see the code working, don't worry, just go, take your time. Automatically the problems will get solved. Okay, so if no one has any questions, I will stop here. So have a wonderful day. Learn, have fun. Bye bye.
Thank you, Madhu. Bye.
Thank you.